I'm sorry if I keep coming to class day after day saying this, but I'm really, really tired. And I can't recollect discussing matrix versions of transformations, have I? Do you guys think...
There was one thing that we did, which I think is probably what you're talking about here, where they took the T of E1, T E2, and put that into a matrix. You didn't discuss it, but it didn't seem too hard, so I just did it.
Well, do you think then, I'll listen to the board. I will answer your question.
Okay.
Can I just go through a little bit of theory first?
Sure.
Just so we know what's all going on. Because I'm getting nervous. I really don't recollect even saying anything.
Yeah, we noticed that
Right.
yesterday.
Just yell at me next time.
Okay.
Now I gotta apologize for being so slow. Let's you and I consider linear transformation. Say from Rn to Rm. T can be expressed as a matrix transformation. In the following fashion, T of added anything like an x bar can be interpreted as nothing more than some matrix times x bar, where this matrix A is nothing more than an m by n matrix in which, column by column, I've got the transformation of these standard unit vectors.
And so the E1, E2, E3, what does the E stand for in those, in that case? Is it just something you're calling your transformation?
I think when I first started talking about Sis's equations, I actually mentioned in class once, we never did anything with it. But check this out, R3. Would you guys agree that this is a basis matrix, by the way? Would you agree that this is the most basic basis for R3?
Mm-hmm.
Yeah, that's good. It's just that when it comes to Rn, I get sick and tired of the notation. I don't want to be writing this, 1, 0, 0, dot, 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 0, n, and then 0, 1, I'm getting tired of this. So I give up. And I simply think of Rn, or at least its simplest basis, as simply containing entries like E sub bar 1, E sub bar 2, all the way down to E sub n bar, excuse me if I'm saying those bars and n's in the wrong order. In other words, E sub 1 is an n tuple with 1 in the first slot, 0s everywhere else. E2 bar is an n tuple with 0 in the first slot, 1 in the second slot, and 0s everywhere else, etc., etc., etc. That's why I have n of them. It's just because we're lazy. We don't want to write all the garbage out. So that's all the E sub I bars really represent. 1 in the I slot, 0s everywhere else. But I maintain when it comes to a transformation from Rn to Rm, I can always find a matrix transformation that corresponds to it. Okay, I'm getting nervous. I'm the one who said it was a theorem. Let's see if I can prove it. For me to convince you for an arbitrary linear transformation, like this one up here, that there exists such a matrix A, then let me play this game. Back in the vector space Rn, the first one, I'm just going to grab an arbitrary element out of there. How about x bar? And let's consider an x bar that can be represented this way. Oh, you know what? I got a better idea. Let me use this new E bar notation. What I'm really suggesting is x bar can be expressed as x sub 1 times E1 bar plus x sub 2 times, well, not that, but E2 bar. All the way down to x sub n times E sub n bar. You guys please stop me at any moment. Is my notation okay? Now, if I were to come in and transform x bar with my understood linear transformation, I'm assuming I've got this. I should have written it down in my proof. I'm assuming I've got a linear transformation from here to here. I'll show you that I can find such a matrix A, and it's going to be this. Well, in transforming this vector x bar, I guess I better be transforming, how about this version of x bar? However, it is the case that I'm making an assumption here, namely that T is a linear transformation, and I've got my linearity properties holding for me. For example, I think T eval of the sum is the sum of a bunch of T's. Oh, by the way, the other linearity property of linear transformations allows me to pull out those coefficients. I guess it means I've got this. And if you look carefully at what I have on the inkboard, I think this is nothing more than the result of multiplying a vector, excuse me, misspoke, a matrix of the form, where the first column is just T eval at E1 bar. The second column is T eval at E sub 2 bar. And all the way down to the last column, which is going to be labeled as T eval at E sub n bar. And that matrix is being multiplied by a column vector. I'm writing it over to you guys. Can I write it shortly? X1 all the way down to Xn. It's just that what you see between my two fingertips is nothing more than what I define as my matrix A. And what you see over here is nothing more than X bar right back. So I just justified for you that I really can't re-express the output of that linear transformation when the input is of anything in the original vector space Rn in this following fashion. Does that make sense? I'm hoping it does. But if that being the case, you guys, what does it really say in English? It's saying this. If you know how your basic items in Rn look like from a standard basis, if you know what they get sent to through this transformation, then column by column, that's going to constitute your matrix transformation. That's all it's suggesting. So now kind of back to number 23.
Well, I was going to suggest maybe doing like 17, 18, 19, one of those, because it would be a good way of actually showing how all this works.
Could I just make one up?
Yeah, or you could just make one up.
Only because somebody
Yeah.
asked, I'm going to answer it eventually. But that means, can I ask you if I could erase the middle board?
Yeah.
Much nicer. You guys, can I ask you a simpler question first? Well, I shouldn't say simple. Can I ask you a prerequisite question? When it comes to the transformation described by this matrix right here, the transformation I'm going to describe for you in a few minutes is really going to map R what dimension to R what dimension? Do you know?
Whoa.
Say that.
Let's give it R3 to R2. No, R2 to R2.
I think it would be R2 to R2, right?
All right, I got an idea. Watch, with my green pen. If I were to multiply
R3 to
this by a
R3.
vector,
R3.
this is going to have to come in from the very first vector space, isn't it? Which
Yeah.
you see green. It's just that this matrix right here is in dimension 2 by 3. So what must the first dimension of this matrix be?
It's 3.
It's got to be 3 for multiplication
Yep.
to be defined, because the number of columns is the number of rows of the second matrix has to be equal to the number of columns in the first matrix. And so I do think this is going to have to be a 3 by 1. And for that reason, I do think that the transformation is going to have to send R3 corresponding to
R3.
I can hear you.
R.
What's that a guess?
R2. Okay.
Okay, you said 2 left over. You know what I think in my head? I say this.
Oh.
The output is going to be another matrix whose dimension is going to be, well, a dimension determined by the number of rows of the first, correspondingly to the number of columns of the second, is going to be a 2 by 1. So I know the output has to go to R2. If you guys want something goofy to remember, you could say this. The dimension of matrix A is the reverse of those things, but it sounds kind of goofy and hand-waving. I just kind of look at where I'm being sent to and where I'm being sent from. So let's give it a shot. to find out what this transformation is, I'll come in and I will simply take T evaluated an arbitrary vector x bar, which by the way is going to give me a product of this matrix right here, 1, 2, -1, 2, 3, 1, times correspondingly 2 by 1 matrix, which has entries x1 and x2. After all, I chose an arbitrary vector x bar in R3, excuse me, jeepers. I think at this point it's just a game of multiplying out the matrices. It's that goofy. And let's see, that's a 2 by 3, here's a 3 by 1. The result's going to be a 2 by 1, whose entries are going to be formed by looking at dot products. So let's you want to take a peek at this product matrix. Identify the entry in the first column, first row. It's obtained by dotting the first row of the first, and the first column the second. But jeepers, that's just going to give me an x1 plus 2x2 minus x3. The second entry in this product matrix is located in the second row, first column, so I don't dot the second row of the first with the first column of the second. But that's just going to give me a 2x1 plus 3x2 plus x3. And that's the result of the multiplication of these matrices, which clearly, you guys, clearly is a 2 by 3. Are you
Now,
there?
that's generally not the way that they want it written. They want it written like, can I show you? Oh.
Yeah, before you do, is that okay?
Yeah, that's okay.
2 by 1.
Or
No,
no, it'd be 3 by 2, or 2 by 1, 2 by 1.
Reasons here.
That's 2 by 1.
Okay, good. This is not a 2 by 3.
Yeah.
Technically speaking, I've got addition and subtraction up here. Do you guys see my point?
Yeah.
This really is just a 2 by 1. Like I suggested, it better be. Are you there?
Yeah.
Okay. Sorry, Brad.
Okay.
I was just trying to make it.
The book generally, write the answer like this. They
Oh,
take you
I
through
get
all
to
this, all these steps, right? And
Yes.
then the book would write the answer like
Boy.
x1, x2, x3 equals.
Well, he's just using row vectors instead of column vectors.
Why is he using row vectors? I asked, why is he using row vectors?
Why not?
Because you're just referring to each of these rows, but
Because.
They're isomorphic?
Oh, definitely not in this case.
Okay.
You guys, he's only writing as a row vector for this reason. He's saving ink space. That's all he's doing. It doesn't make any difference. In fact, Chris, I thought you asked this one day, like weeks ago. You said, well, can I write a column vector of dimension n as a row vector of dimension n? I said, sure, that's all equivalent. It's fine. But I'm being honest. I don't know the answer to my question, but I assume it's just because he's saving printing space. Nothing more.
so
And Brad, I think the only thing I violated in terms of what the author writes, I just showed you clearly what the input was. I didn't think I had to because of my
the author actually does both. He
So
shows
he's
you
gonna
both.
change his way he does.
Yeah, so he does everything that you've done there, and then he also does the bottom.
Gotcha.
But-
But I just think this is a restatement of what I wrote at Party Down.
So, do you really care whether
I
you
have
put
no
that or
preference
not?
whatsoever.
Yeah. Okay, so we could just do what you did and ignore the bottom portion.
And I'm certainly hoping you agree that they're the same.
Yeah, well, yeah, I know. That's what I was kind of confused about when I was looking at the book. Is it looks like he's just restating the exact same thing.
Yeah, he is.
Okay.
Chris?
I have a question about mapping.
Yes, please.
We were talking about the range, but the range isn't. You often say, this transformation is a mapping from some space to another space, but we never say the range is that other space. We say the range is a
Whoa,
collection. of
what a good
different
point.
spaces. So I'm wondering why we don't just specify the mapping as from one space to that range, because that seems more concise.
Because it is the case, and we did prove this, it is the case that the range is a subspace, second space. And so a lot of times the second vector space is a standard vector space. And the range ends up being a subset of it. And it's just easy to talk about that standard vector space for which the range is a subset and also
Well,
subspace.
it's a qualifier, where we know that we're entering, maybe the transformation is going from Rn to Rn. We don't even need to talk about Rn that much, we just know it's Rn. Does that make sense?
No, it does. I'm trying to find a better way of saying what I'm trying to suggest. Let's for a moment do it your way visually. So I've got a linear transformation T mapping from some vector space V, G for G. Oh, that was so much better. So this.
It's almost Christmas.
It's almost Christmas. Let's see how fast you guys are. Look at my picture.
I'm trying.
Wait, look at my picture. Is that an alternate?
Drink too much caffeine.
See, I think the answer is I don't know, because I don't see what the other vector space is for which the range of the subspace. I mean, if I gave you this picture right here. Now, can you answer my question quickly? Is that an onto transformation?
Sure.
Yes.
I would say you can answer the question quickly, but the answer is no. No, because the range is not always a vector space.
Yeah.
And so I think sometimes it's kind of nice to do that, because technically speaking, I'm often worried about whether or not these two spaces are isomorphic anyways. And so visually speaking, I kind of like this, because if there's an isomorphism, it means two things. Number one, I get to take this green set, I get to blow it up, and it's as big as V. If this were an onto transformation, this green set would fill up all the W. And if this were a one-to-one transformation, that also means that all that garbage being sent to zero element, the second vector space, shrinks down to just a singleton set, namely or specifically the zero element of the vector space V. And so visually, I think it's so much nicer when I actually draw that second vector space for which the range is a subspace.
Okay.
I can't come with anything better than that. There are times where I think this range, or excuse me, this W would be too difficult to really look at. And I will violate what I just said and use Chris's approach at times. In particular, when it comes to something called a Laplace transform, whatever that is, I will play your game. I'll just give up. I don't even care what's over there. I just only want to talk about the range.
We're not doing that this semester, are we? Oh, gosh.
We are.
Oh, yeah. Laplace transforms, you're going to love it. It's going to be your best tool this semester. So, you guys,
I don't mind this with the initial value problem.
you know, it's sensitive. Okay, I can see that. I can see that.
Yeah, I mean, it starts off and you just gotta find the basis, right? So this is,
Yeah, that-
this is
my
previous
question-
chapter work.
The question was part B, is how do you figure out what the transformation actually is, like what the mechanism is that gets you from
Oh, man, I remember this one was
basis to
just,
your transformation basis.
I think this is what I did.
I want to do it.
Did all that.
Because I think this question is slightly more sophisticated. Can I just do one more example before I go over there? Just one more. Suppose, let's see, example 2. I'm just double checking that I answered my question. Yeah, we did. Sorry, I told you I'm really tired. Example number 2. Yikes. Suppose. I've got a transformation.
Where's this step that really bugs me?
Margarita R2.
Is it this part that got you? How to get something out of that?
No.
That's described as follows.
No, I didn't get to, okay, that was the part that got me. Can you do this problem today though? Because there was one part that really just like
Oh, we'll do it right next.
Okay,
Call this example
okay.
number 3.
example 3.
Yeah, there's only one thing missing here that I want you guys to appreciate how relative narrow to the board, that is not 1, 0. This is not 0, 1 as an ordered pair. And that's the real problem here. But come back over here first. What if I told you that the following is true? I'm being honest, I'm making these numbers up out of complete thin air. then can you tell me the corresponding matrix that describes this transformation? Hold up, I'm missing a word. So what is that? Well, relative theorem I just gave you, I think is immediate. I think I just simply have that A is going to be equal to a matrix, where column by column I have the transformation of this vector that I called E1 before. And the next column is going to be T evaluated at this vector. Am I totally obliterating my parentheses? Cheers. And then finally, the third column is going to be T evaluated at this vector. And I guess in the end, what that really means is that column by column, I have entries. Is that a -1, 2? Is that a 3, 5? Is that a 4, 1? Do you guys agree?
Yes. Yes.
Sorry, that wasn't a very significant question, but now I can go to number 23, or my example 3 if I can call it that. So, coming back in, I think over here, it is the case that T evaluated 1, 0, and T evaluated 0, 1 are given as, what was that, 2, 3, and -1, 1.
Except it's not,
Is that what?
it's not 1, 0, and 0, 1.
Beautiful. I made a mistake. Technically speaking, it's not true. If it were, I'm done. I just list these in my columns. We're in business. So you guys are right. I am wrong.
But it's
I
the
did not-
transformation of V1, which is not 1, 0. So, yeah.
So bottom line is I don't know what 1, 0 gets transformed to. But check this out. I do think T evaluated 1, 0 could be interpreted as T evaluated, I don't know, some constant, I'll call it C1, times my first vector 2, 3. Plus, can you read my sloppy writing? That's a C. Plus my T evaluated, excuse me, I still misspeak.
Oh, wait, no, it's not going to be the 2, 3, right? Because that's not your first vector, because T is going to be evaluated at V1, and V1 is 1, 1.
Well, I don't know that yet, but you're right. I did make a mistake,
But,
didn't I?
well, you do know it because it's given in the book.
What's given?
V1 and V2.
They are?
Yes.
Yeah, V1 and V2 are given.
V1 and V2 are given, but the transformation is not given.
My apologies. So part A,
Yes.
he already gave you V1 and V2 bars.
But it tells you what the
Jesus.
transformation is equal to. The transformation is equal to 2, 3, and -1 and 1.
I understand completely. So what you're really saying is this. I have that this vector, 1, 0, could be interpreted as some constant C1 times, what was V1 bar? 1, 1.
Yeah.
And C2 times the other V2 bar was given as a 1, -1. And you guys, if I can just find C1 and C2, I think I'm in business. Well, technically speaking, T is a linear transformation, so I guess I can break it up using that first linearity property. Actually, there's the second linearity property for linear transformations tells me I can pull out these coefficients. Oh, by the way, when it comes to transformation of 1, 1, it was given as, if you don't have your text, it was explicitly given as, there it is over there, 2, 3. Likewise, C2 is given as, jeepers, -1, 1. Now let's see when I just find out what those constants C1 and C2 are. And to find out what the constants are, what do you want me to do?
You can make a matrix.
What matrix?
Oh, you augment the matrix. Of
You'd augment it with your.
What?
I think you'd plug in an
What you
x1,
want.
x2, and you'd solve for your c's
But
in
you're
terms
saying,
of x.
saying C1, 1, 1 plus C2, 1, -1.
So-
Just make sure I'm writing it down correctly.
So you'd have your first row of first column of the matrix would be 1, 1. Second column would be 1, -1. And then you'd augment it, and you do an x1. No. Do an
No,
you
x1.
augment it with what you
And
want
X2.
your original vector to become.
What I want it to be.
Yeah.
1, 0.
Beautiful. Did you guys see his point?
Yeah.
You take away the transformation, take away the t business, doesn't it just say c1 times this plus c2 times this is equal to that? So technically speaking, I'm looking at linear combinations of these base elements giving me that element. So I think in my very first row, I shouldn't have a 0 at the end, I should have a 1. Did you guys see my point? And if you do, shoot, we're done. Piece of cake. Let me multiply the first row by -1. Add the second, and use my new second row, but I'm only doing it in my head. I'm not going to write it down. I think that'll give me a 0. Is it a -2, -1? And Brad, just tell me if I don't get what you get.
Well, book did something different.
Did it really? What did he do?
He used x1 and x2
Show
instead
me
of
where.
zeros. I know that's not the proper form, but this is the final answer that he got. And then he went through and simplified it, set it up like that, with your v1, v2, because that's what we're multiplying this term by. And then we ended up getting a transformation at the end that's like this. But
Okay.
he was able to transform that.
It just feels so clunky. Because you know what I was trying to do? I was trying to exploit the theorem I just gave you.
Okay.
Let's see if we get the same answer doing it my way.
Okay.
Does that give me 1, 1, 1? You guys, I'm sorry to bore you with the arithmetic. I'm almost done. Just one more step. Does that give me this? Sorry, I gotta slow down. Does that tell me I've got a positive 1/2? In other words, C1 and C2 are equal to 1/2, but over here, that means the output of transformation, you've added 1, 0 is going to be my 1/2. 2, 3, plus 1/2 times -1, 1. Or better yet, is that simply going to give me, oh, you guys again make me do all the work. Is that a 1/2? Is that a 2?
Okay.
So I think when it comes to the matrix transformation, my matrix A is merely going to be a 2 by 2 matrix where the very first column has entries 1/2 and 2. Oh, shoot, I blew it. I didn't cover the other entries, darn it. I gotta stop. Take a break. But I need some room. Can I erase this or manipulate it? Now I want to know what happens to this one. In other words, let's yet again find my constant C1 and C2. So I guess I'll stop here. Make the proclamation that the corresponding augmented matrix comes from this equation, which is going to give me this column. And only because it's that last column that's going to change, can I just erase them and rederive what those entries are going to be? And let's see, what the heck am I doing here? -1 times the first plus the second is the new second. I guess it's a 1. Next, multiplying the second row by -1/2 gives me this. And lastly, -1 times second plus the first, use that as my new first, it's going to give me, is it a positive 1? And that being the case, I maintain C1 and C2 hold those two values of positive 1/2. And I said -1/2, excuse me. Or more collectively, that's going to give me 1, 3/2 minus a positive 1/2, -1/2. Finally, should I say, that's going to give me this following ordered pair. 1/2, 1.
2.
Minus
Because 4 over 2 is 2.
No, you guys, I think I've got multiple errors. Looks to me like I took the -1/2 and distributed it in as -1/2.
Should be positive.
Yeah, I'm so sorry. That is my mistake.
Okay.
Does that in the end change my answer? Is that going to give me a 3/2?
Mhm.
Positive 1?
Yep.
Just please double check my arithmetic. That means the second column in matrix A is going to have entries 3/2 and 1. Now, you guys, technically speaking, you know what? I have not answered the question. You know, technically speaking, he wants me to value this transformation on this ordered pair x1, x2, which is an arbitrary element in the first vector space. So let me show you what it is. I think it's nothing more than my matrix A times x bar. Or in this case, that's going to be 1/2, 3/2, 2, 1, multiplied by x1, x2. But that ends up getting me, let's see, it's a 2 by 1, isn't it? Here's a, I misspoke, boy, it's 2 by 2. This is a 2 by 1, so I think the resulting product matrix is gonna be a 2 by 1. Let's just crank it out. I think it's gonna give me, let's see, let's dot the first row the first with a single column the second. It's gonna give me 1/2 x1 plus 3/2 x2. I think dotting the second row with a single column the second matrix is gonna be a 2x1 plus x2. And Brad, tell me, is that the same answer he gets? It better be.
Let's double check. Oh, so this is,
This is number 23, section 5.1.
yep,
Oh, good. So he agrees.
yeah, he just,
Just did it a different way. I just
well,
wanted to
yeah.
exploit that last time.
Just the solutions manual did so much more work.
Did it really?
Yeah, but I think this way is a lot easier.
And I know I get,
And what's really weird is the next problems that we go into are exactly what you've been doing, so I don't understand why he took the long route, but he did.
are you recording this?
Yeah.
So, you guys somehow got a hold of the solutions manual, right?
Yes.
I know how you got a hold of it. I don't look at it. I don't know how he does things. I
Yeah,
apologize.
yeah.
So when I come to class, I'm just
I,
doing whichever is
yeah,
comfortable.
I bought it off of a guy behind Jack in the Box.
There you go.
Yeah.
That was it. Oh, by the way, I still haven't answered the other question. To find out where 4, -2 gets mapped to, am I not just going to say it's a 2 by 2? I take it back. It's going to be a 2 by 1, which is found by looking at 1/2 times x1 plus 3/2 times x2. The second entry is going to be 2 times x1 plus my x2, or shall I say in this particular case, is this 2 by 1. It's, I can't do it. -1, +6, I hope. As usual, just check that arithmetic.
Okay.
Anyway, I apologize for that. I apologize in the sense that I sent you off doing homework, and apparently I just didn't discuss it.
It wasn't very hard.
No, it's just more solving systems. It's just that I think you need to keep the order straight. And I think it might not have been natural, the way I said, oh, column by column, these are nothing more than the vectors which identify how E1 bar and E2 bar were transformed. If I could be that abstract. All right. You guys, since you stalled me anyway, anything else you want that you want to clean up?
I think so far that's about it.
So far, so good.
Yeah. For me, at least.
So do this for me. How would I determine if a matrix, oh, excuse me, I misspoke. How would I determine if a transformation is 1-to-1? Yeah, see if the kernel is equal to the singleton set, namely 0 in the first vector space. How would I determine if, I shouldn't have asked the question, that was a bad question. Give me one way I can determine the range of a transformation.
You add it with
It's the thing where we have the kernel plus the range is equal to the dimension of the
dimension.
Dimension of the kernel.
First vector space.
First vector.
So you really meant the dimension of the kernel plus the dimension of the range equals the dimension of the first vector space. That's a general nullity theorem. And if you know the dimension of your kernel, you know the dimension of your range, which you typically would, because you've got a list in front of you, then you can find the dimension of the range. Well, that doesn't tell you what the range is, does it? But if with a general rank nullity theorem, you can determine that the dimension of the range is the same as the dimension of the second vector space, the W usually I have written on the board, then you know that the range is all of W. And that also, by the way, would be probably your most prominent way of determining whether or not your linear transformation is onto. And if your transformation is both 1-to-1 and onto, I sometimes say that that linear transformation is an isomorphism. And if I've got an isomorphism, just like back in Math D, it means I've got a 1-to-1 function that can have an inverse. And so, let's get some practice at finding inverses.
Which chapter is the general rank and nullity problems? I only got through 5.1 last night.
Let me just check the titles.
Okay.
So the kernel and the range are in 5.3.
5.3,
If you want to talk to about one-to-oneness and onto-ness, they'll be at 5.4.
5.4.
And I know I've already talked about it, I just didn't finish my discussion, so I don't think I signed anything in 5.4 yesterday.
Yeah, I think you assigned us 12.
Oh, well, that's one silly question.
12, yeah. One loan.
That doesn't
Probably,
qualify as homework.
Oh, really?
This is one question.
Parentheses. That's what the parentheses.
What's that?
Parentheses.
I'm so good with parentheses usually, it's just something going
Yeah,
wrong.
I know. Watch, I'm going to do that on the exam.
Sorry, so slow, you guys. I know I haven't asked a question yet, but consider this transformation. How do I do that?
So,
How do I answer the question? And don't be careful. Be really stalking. Just in general, how would I answer the question? Mike?
See, zero vector from P2 maps to zero vector of W.
I just did. It does. But does that answer the question, which is determine the kernel? Someone. What's that? Putting you on the spot. Daniel?
Set the kernel of some arbitrary element in P2 equal to the zero element of W.
You mean the transformation of an arbitrary element in P2
Yes.
to the zero in the second vector space. I agree completely. Actually, I might be writing too much just to show you what he's saying. Let's see when I consider the kernel of T and what it actually should look like. I think this is nothing more than a collection of all vectors in the very first vector space, that P2, such that they get transformed to the zero in the second vector space. Which, by the way, looks like that. Or shall I say, I'm looking for all the transform elements in the first vector space, which, by the way, look like this. You guys, I want to rephrase this. I'm getting too sloppy with my notation again. I really should be saying where the transformation of that little p and big P2 is going to end up being nothing more than the 0 2x2 matrix. Nothing more. But cheapers, you guys, doesn't that suggest that I've actually got a system of equations, namely a sub 1 plus a sub 2 is equal to 0, and a sub naught, whoops, I should slide that over, hold it. A sub 1 plus a sub 2 is 0, which is what I said. And then the entry in the first row, second column, which is this, is equal to 0. And finally, the last entry is equal to M. And put it in an augmented matrix. Does that look like the following? Is that a 1, 1, 1, 0? A 0, 1, 1, 0. And then finally, is that a 1, 0, 1, 0?
In the second equation, in your
Yes.
in your system, there should be a a sub naught plus 2 a sub 2.
Should be 1,
Oh,
0,
thank
2.
you. My 2 got absorbed by A, didn't it? And that was an A sub naught plus A sub 2. That would be right here. I missed my 2. But that means down here I missed my 2. Thank you. And solving the system should be a piece of cake, I hope.